Perfect. I can hear you all. Thank you, Christy, for the demo. I really wanted to be there with all of you guys at GitHub. I guess some of you who attend events often probably see me around there. Love the office, but just today was working on a really tough problem and cannot make it. So with AI in the last couple of years, we saw models getting bigger and bigger, and most of them would still focus on English capabilities. And in our case, we've been working on AI-related infra for the last 8.5 years. And in that period, we've kind of saw how hard it is, like, yes, to build the big models, but it's even harder to build small ones. It becomes even harder if you try to make them multilingual or multimodal. So we generally aim for the hottest competition. And for the last couple of years, we've been participating in the race for some of the better open source multimodal, multilingual models. So that's what Christy was showing off today. Some of those ideas are not really new. I think most of the innovation happened between 2019 and 2021. We don't really have too much to claim there or to brag about in terms of research, but I really enjoy some of our models, and all of them are available under Apache 2 license. So you can easily use them in your applications. But one of the most interesting models that we trained was this multilingual V2 model that we've published, I think, around a year ago. Um, and the reason it's interesting, in a size of just a couple 100 million parameters, so smaller than comparable inaccuracy clip, we've managed to feed amazing multilingual capabilities, and that covers almost all widely spoken languages. So this includes languages like Hindi, like Arabic, like French. So in Arabic, our recall at one, which is the ability to find the most appropriate image for, let's say, a text input, supersedes open clips of comparable size, actually 50% larger one, by over 10%. But the more interesting part about those models is that we have to be very parameter efficient, but also data efficient. And we cannot always train on a cluster of 1,000 GPUs. So we've ended up training most of our models on very small but very high quality data sets, generally with less than 10 million images. And I think the one in this table used only 4 million data samples, actually image samples, to achieve this level of accuracy. So at this point, this probably sounds like snake oil, but it gets worse. So in reality, it's not just like those 5 languages. The model was trained on 20 languages. And unlike most models, this specific model was trained on a balanced set. So the number of samples that the model sees across every language is identical. So we show equivalent number of samples in English, in German, in French, in Chinese, in Hindi. And to avoid enumerating all the languages on the list, I would also mention that we sometimes show very uncommon languages. So languages like Armenian and Hebrew, they are not as common in broad data sets like Lion. But if you heavily curate your data, you can actually find enough data to make the models competitive even on those low resource languages. So we've trained several models like this, ranging in size from 79 million parameters to close to 400 million neurons. And we also wanted to make them widely available for the whole ecosystem, not just a small sample of us who write Python. So the models were originally trained in PyTorch. They're also available on Hugging Face in ONNX, which is the Open Neural Network Exchange format, and CoreML. The beauty of having ONNX is that ONNX is the most widely supported format for neural network exchange. It has runtimes and SDKs for several programming languages and different vendors of hardware. And if you install ONNX even in Python, you don't have to pull all of PyTorch as a dependency. So pulling PyTorch as a dependency requires you to have the CUDA runtime, the PyTorch libraries, the front end and the back end, which easily requires downloading gigabytes of data. But if your entire model is 20 megabytes or 50 megabytes, pulling a 2 gigabyte runtime is not always an efficient way to start your pipeline. Aside from like having all those frameworks that we support, we also support several SDKs and several bindings for the UForm library. So if you follow this URL that Christy also shared, you'll see the library. And the same repository contains the source code for Python, for JavaScript, and Swift for the models, including the embedding models and some of our multimodal generative models. And just as Christy said, some of those models also support Matryoshka-style embeddings. So you can kind of slice them into parts, keeping only the first 64 dimensions in some cases, and still getting competitive results. And as an example, I put together some of our libraries in this demo written in Swift that is also available on GitHub. So it can run on your device. And because the model is so lightweight, the model used in this demo, I think the weight's only 40 megabytes. It can run real time on video input, even from a camera feed. So you can have your own wearable device, which you probably all own already, which is your phone, without the need to buy some kind of a wearable pin, and already get the benefits of real-time AI in your mobile devices. So everything until this point was a bit of marketing, I would say. And the reason this actually works is of this simple trick that is called mid-fusion. And I think there are two families of models that are somewhat popular that implement mid-fusion. Some of those would be our models, and the others would be ALBF by Salesforce, also shown around the same time. So the original clip models are like open clip models that are widely popular. They use a late fusion approach, meaning you have two towers of transformers of different modalities. You propagate the signal through them, and later on top, you add contrastive loss to synchronize the representation spaces of those two separate models. So you originally trained two separate models, and then you synchronize them together. The approach that allows us to make the models more data and parameter efficient during training is mid-fusion. So some of the layers of the transformer towers are shared between the two. So this is kind of a step in the right direction, but the ultimate goal of all of this is to get to early fusion. Early fusion would imply having one same model, one same tower, processing both the visual input, the textual input, and ideally more modalities down the road. So far, we've got to mid-fusion. I think a lot of the interesting work in this direction and some of the first interesting proposals were mostly in 2021. Some of them came from DeepMind's paper, Decoupling the Role of Data. And they suggested several approaches to multimodal attention, some of which we tried to re-implement at our team, and most of the time we failed. And then we started seeing like more of those comparisons between binary classifiers and contrastive losses. Several papers were published until 2021. I think most of them followed the same idea of using attraction and repulsion, pulling points in the high dimensional space closer or further from each other. And unlike most people who work in multimodal perception, my interests come from graph theory. And in graph theory, similar approaches have been used to draw graphs as early as 50, 60 years ago. So I personally attribute this approach to Tuta in 1963, who published some of the first papers describing on how to draw graphs using physics-inspired systems where you pull points together or just push them far from each other. And if you read those papers, you'll see like so much shared understanding between what we're doing in some of the multimodal perception problems today and what was done decades ago. Still, all those approaches shared several problems. I think if you go outside of image and text pairs, you'll quickly find yourself struggling to find the right training data. Today, it's a bit easier than it was 3 years ago. But still, when you're training several separate models and then you try to synchronize them together, the computational cost of doing it is just tremendous. That's why companies who follow this approach would generally use thousands of GPUs over weeks. And then you get all those problems with evaluation because the models trained on the original data saw completely separate data distributions, and it's very hard to understand where they will fail to synchronize the signal. Until maybe 2 weeks ago, when we saw a paper published by FAIR called Chameleon, Mixed Model Early Fusion Foundational Models. So the timing of this meetup is just amazing. we just saw the first new big step in the direction towards multimodal AI. What the team accomplished, they trained a single autoregressive model to produce both textual and visual content. And this involved this creation of the special like image detokenizer. Sadly, there is no code available. The weights are also not available yet. And we don't have too many details about the image detokenizer, but the work comes from the team that previously delivered a lot of really interesting models in the multimodal space. And assuming in the last 12 months, we saw several papers showcasing how to produce embedding models or like embedding representations out of autoregressive models. I'm pretty sure the same approach or the same model that would be published with like this autoregressive design could be used for embeddings, very high quality embeddings down the road. The model that was suggested features 34 billion parameters, and it's competitive when compared to 1 trillion parameter models, including GPT-4V and Gemini. And what we see on a second table here is human evals, where in a lot of cases, all three annotators agree that Chameleon captions or question answers were better than those of GPT-4V and Gemini. And a lot of this improvement is probably attributed not to the quality of data, but to the architectural improvements that are suggested in the paper. Until we get there, until we get to the weights, the best we got so far in terms of multimodal generation, at least within my team, we were able to use a hybrid approach, combining several models, including our encoder models, actually the larger ones, not the ones that are published. So I think this generative pipeline using UForm Gen 2 models overall is about 1.2 billion parameters. It uses the Quen 500 million parameter generative autoregressive model and a 700 million parameter encoder, which is like one of the larger ones you would see in such hybrid systems. It produces very high quality descriptions and question answers for its tiny size. And we saw people running them even on watches. But to be honest, I'm pretty sure that early fusion model or like shared model that captures all modalities at once would be far superior in design to this. So my expectations for this model that we just saw from FAIR is that we'll see several new designs coming out, ideally not just 7 billion parameter model, but smaller ones that would blow all of the competition out of water. And the models, if we succeed in making them even smaller, I think 100 million parameter early fusion model, if used for embeddings, can be competitive with a billion parameter open clip model. So this is the progress we've seen in the last couple of years. On the implementation side of things and the deployment, this would imply several things. First, we would be able to squeeze over 100,000 inferences per second, making this kinds of models much more applicable in production. So much so that we'll be able to run this on parallel video streams from thousands of cameras or mobile devices in real time. What it means for search, which is my favorite problem space, is that the embeddings will keep getting smaller. Some people will follow the quantization route. Others will be slicing off dimensions similar to Matryoshka. While Christy was delivering her demo, I was getting the most recent numbers from the search engine that we implement and also share with the community, USearch, which is powers some of the largest databases and several database brands, including both standalone databases like ClickHouse and in-process databases like DuckDB. If you just use 256 dimensional embeddings like the default ones produced by UForm, in Float32, you would get of the order of 189,000 queries per second with close to perfect recall. This is measured on dual socket Sapphire Rapids system. So Sapphire Rapids is fourth generation Intel Xeon with 64 cores. So dual socket means 128 cores. With Float 16, with those kinds of nodes, what we can get is 351,000 queries per second with 99% recall. The reason it's so important, like, to mention what kind of devices you use for those benchmarks is that Intel sub-5 rapid CPUs support AVX512 FP16 instructions, which allow dot products implementation in hardware for half precision numeric types, which includes float 16, obviously. And it's also just as fast for BF16, for the brain float 16 format. And then the intuition that a lot of the developers would have is that it should work even better for int8, which in reality is true if you just benchmark the kernel itself, how fast the dot product can be implemented. But the problem with all those approximate nearest neighbor search data structures is that the number of computations you have to perform is somewhat proportional to the quality of the metric you use. And if your quantization scheme was too bad and the original embeddings are not really suited for int8 representations, you may end up walking around the nearest neighbor search graph for way too long, and your overall throughput of the system would be lower. So even though modern machines are much better at handling int8, in many cases, with most models that you use today, you have to test your own luck and perform benchmarks before you can implement int8 in production. And then potentially the most interesting part is like B1 binary representations. On some of the embedding models, they work quite well, which is true for coheres embeddings, for mixed bread embeddings for text. But I'm not aware of multi-modal models that would work fine with those kinds of representations. So with this, I gave you the gist of what it means to run small multimodal models at large scale. So take tiny models, use Onyx as runtime as it's compatible with every piece of hardware and software, quantize the representations into float 16. In some cases, you may be lucky with int8 as well. And make sure to check out some of those libraries. All of them are heavily community driven. We maintain all of them. This includes fast nearest neighbor search engines, very tiny embedding and generative models, networking stack that is up to 50 to 70 times faster than the libraries most Python developers would use today, and even string implementations. So if you're in the AI space and you need to work with trillions of tokens, as we sometimes have to, just replacing the Python string and its dot split functionality for processing new line delimited files can accelerate your pipeline by a factor of 3 and reduce the memory consumption by a factor of 10. That's why we implemented for our own research, but we are very happy to share it with community. And without further ado, I will leave the stage for the next speaker. Thank you. Any questions?
Testing, maybe?
Testing.
There you go.
How does
Maybe it works.
does it work? Yeah, it works. How does the encoder model compare to something like SIGLIP versus CLIP? Because I saw that CLIP, the comparison was given.
Yeah, so SIGLIP is a nice model. I'm not sure we have recent evals against that model. So it's like some of the benchmarks that we've shown, especially for larger models, are a bit outdated. It's just that in the tiny model space, the releases are so infrequent that we just release the model and then spend many months working on the next generation.
Okay, thank you.
Well, if you have additional questions, talk to Christy afterwards. Well, I guess one quick one, and then we'll jump. Go ahead.
So I'm just wondering, for the semantic search, when you have to put the embeddings of an image and the query and NLP in the same dimension, as you said, nearest neighborhood search is expensive. Are you doing any transformations to store the data for encoding, and are you storing all the data as it is? And also, isn't it expensive to store everything together in the same dimension? And then dimension may overlap also.
So there are a few ways to answer this question depending on how I understand it. If we think about 256 floating point numbers, the amount of information that you can write into such a volume of data is just tremendous. So it's 2 to the power 16 by 256 if you use float 16 representations. So I believe the amount of raw information that we can encode into this many dimensions is more than enough for high quality semantic search on a scale of up to maybe at least 50 billion entities. That's kind of where we've stopped benchmarking. Next year, we'll probably try to scale to up to 1 trillion entries per node. And in that case, maybe we need more dimensions to differentiate data properly. As for combining just signals from different modalities, with multimodal models, the goal overall is just like to build a shared vector space for all the semantics that humans are familiar with. And this includes images, videos, audio signal, everything like this, which would potentially lead us to better, more competent AI down the road, because we can definitely, as humans, we learn better from many modalities. Children recognize concepts faster when you show them images and text next to each other, and they relate information from different modalities and infer concepts. With AI, hopefully the same logic applies. But if for some reason you don't want to mix information from different modalities into the same vector space, one of the features that we've built into USearch is support for JIT-compiled metrics. JIT stands for just-in-time compilation, and some of the research teams in larger AI labs use our engines just for this reason, to be able to do research in representation learning. So that what that can allow you to do is just take a separate text model like BERT for textual content and produce embedding for your text, and then use a separate vision transformer for your vision content. So you end up with 2 different embeddings from 2 different models, potentially for the same entity. Like if you have an e-commerce store like eBay, you have the visual depiction of the product and you have a textual description of it. Instead of producing 1 embedding, produce 2 for the text and for the image, concatenate them together, and then define a custom JIT-compiled metric, like a user-defined function, of how to compare those objects with each other. Maybe even with a custom scoring function saying that the image has higher weight than the text during the search queries. So this is potentially during clustering problems, so clustering tasks. So this is one of the things you can try to do if you're using those libraries and have issues combining everything into one modality. Let me know if this answers your question.